use ODE. I've been trying. It's so you sit there and it's deep or even then you like this crash to go into it. It takes 1,000 calories, rice and beef. Protein. These are actually take care of those huge. Like yeah, sometimes you like say do hello like rice so long with ground beef. That's like a staple. Right? And it just knocks me out. Knocks me out. I'd say you see that Walmart was selling radioactive shrimp? It's best buy Walmart's. I deserve that shit. Radioactive shrimp out there. Walmart was selling radioactive shrimp. No. It is. Silent. You understand that? Shrimps are fun food. I think you can start up. So we are reviewing the modeling. When you do modeling, essentially what you use, Bischoff law and Newton. Okay, that's what the truth ones that you use. And ENF, interface. You end up with ODE. You write the first thing comes out as ODE. Okay. Then you have to decide what model would you like. There are three models that you have learned in your undergraduate. Transfer functions, which is essentially primarily your education is focusing on transfer functions. Impulse response, not much. The utility of the impulse response over transfer function, I would explain to you. And the status response. So three things you have to, all of them comes from ODE. I already went from ODE to transfer function in the previous lecture, okay? In order to go to transfer function, you have to assume, anyone? Relaxes, otherwise you cannot go. Okay, can you just make, you have to have linear, you have to have time invariant. LTV doesn't have a transfer function. Linear time varying doesn't have a transfer function. Okay? So first you have to say, is that linear? Is that time invariant? Yes, then there is a transfer function if you add relaxedness condition to it. Otherwise, no. Okay? Otherwise, it's ridiculous to something that is not relaxed and you have initial condition or there is energy. You don't have a transfer function in that sense. Okay? We did this. Last time we started the state space. Remember that in the lecture last time? A state space, yes, you can, I proved that it's a special case, it's just a U. And the whole idea is trivial, right? You can look at this and say, well, algorithm, no memorization, okay? Do not memorize anything. That's my advice to you. If you want to be an engineer, do not memorize anything. Learn. concept, idea, what am I doing, a roadmap, okay? Memorization is irrelevant. Actually, is really work against you. Because what it does, it makes the assumption that, hey, I know something. And unfortunately, it's not true. Okay, so the idea here is, look at your ODE, See what set of data do you need. That data is a state. Okay. What did I do here? I look at my ODE. I need, in order to solve ODE, you have had this, whether it's ODE 315 or, is that 315? Yeah. You have to have initial condition. Nth order ODE needs n numbers. Okay? See what are they? Why at the time that you start 0? Why dot you have to know? Why double dot? Just think about what you need to know. That's what I listed here. The list of the stuff that I need to know in order to solve my ODE. This is your data, the constantly I refer to it as a data. You need a data. Call it a state. You're done. Then you say a state space is an evolution of that data. Evolution means what? Change. Change means what? Derivative. Take a derivative of this, and derivative has to be, when you take it, you do some algebra. It's a linear, has to come linear combination of other state, of the state, and input. And then you put in the matrix form, it's called x dot equal ax plus bu, y equals cx plus d. Is that clear? So that's what I did. Then I start taking derivative of it. Up to here, it's a linear combination of other states, so no problem. For this one, I had to look at my ODE and figure it out, and I found that derivative of x hat is a linear combination of other state and e. Make sense? Then put them in a matrix form. This is the lecture from bathroom. Okay, this is your A. One super diagonal at the last row is a coefficient normalized by AN. Okay, that's the last row. And then B 0, 0, 0, 1 at the end. 1 over AN, so to normalize. Okay. C is a Y. Y was the x1. So you say, I'm going to pick up the x1 from the state. How do I pick it? 1, 0, 0 times the state gives you this one. Is that clear? So always this roadmap, no memorization. Think about data that you need, how many that you need. That would be the dimension of your state, whatever the number you need, and do it. And then we went to the general case as well. This is the choice of a state I made at this. Let's look at one. I think I don't have to go through this. I'm going to do the example as well. When you get to the ODE, figure out the data. And that data is a state. Take a derivative and convert it to a state space model. Okay? Other things that we discussed is a non-uniqueness of a state space. Right? Non-uniqueness. Let's just, a state space model is non-unique. Engineers always do this. You give them a model, they have to come up with a good model for a particular design that you do, whatever that design is. So they utilize this all the time. So if your state, the data was X, some non-singular transformation can occur here. Input, so n by n, non-singular. You don't use any data. Knowledge of X is equivalent to the knowledge of X hat. It's a one-to-one mapping that is non-singular. If you know X, you know X. If you don't know X, okay, use that. You use it for what purpose? To create new A, new B, new C, new D with different architecture. And that different architecture help somebody who is doing signal processing, etc. Okay? You don't see those things in your undergraduate, but I strongly recommend to you, okay? For those of you who are not like a degree oriented and you are skill oriented and you want to think about your job, its future, etc., take 501, learn state space model, because you have to deal with it. Okay? So we went through this. So you see, when you do this, this is new state, AN. New state model, AN, new A, new B, new C, new D. You change A, B, C, D. In output relationship doesn't change, but you change the model. You create a model that is useful for the purpose that you are doing. Okay? The various architecture of this model, they refer to it as a canonical form. There are all sorts of canonical form for various design. You see it in a Azure program or when we do the MIMO design. So here I refer to it as A hat, B hat, C hat. So model from A, B, C turned out to be A hat, B hat, C hat. This is your new model. Okay. This was past example. Suppose somebody gives you this model. This is your A, this is your B, this is your C. A looks like this, 0, 1, 0, 0, blah, blah, blah. Okay? I change my state with this matrix. This is your T, non-singular matrix. Here, guess what? I got the new model. Look at my A, very different from this guy. Look at my B, very different from this guy. Look at my C, different from this guy. So non-uniqueness of HC. Okay, so that's the state space model. Now let's talk about going. Now you understand how to do the state space model transfer function. Suppose I have a state space model. I want to go to transfer function. Okay, just moving from state space. Like you are here. Now you know this app. You learn this. If somebody gives you this, you can go there. Now I want to go back to this. Somebody give me a state space model, I want to go back. Transfer function or ODE. Okay? So we want this. Very simple. Take a Laplace transform. Take a Laplace transform. You're in time domain. You want to go to transfer function? Take a Laplace transform. However, remember X is a vector. N-dimensional vector. When you take a Laplace of this vector, it would be Laplace of each component. Okay, so you need to make one assumption in order to go to transfer function. And that would be what? Relaxedness. X of 0, you have to say is equal 0. If you say equal 0, then the Laplace of this is equal to SXX. There's no initial condition. Is that clear to all of you? No? Okay, if somebody gives you f of t, okay? And then look at derivative of f, call it f dot. What's the Laplace of f dot?
S f of s.
No. Minus?
Right, the initial condition.
Do not forget, it's not true. It's not true. Okay? It is true if you put it equal 0. of 0 is non-zero, that's not true. So when you go from here to here, I'm assuming this x at time t is 0. X at time t equals 0 means what? Means relax, there's no energy in the device. The data is 0, x is data. Time 0 is a starting point of your, that means you start with 0 data. 0 data means no energy is stored in the system. Therefore, the board relax. Make sense? Are we good? So I make a relaxed assumption, I go to this. Here is x-s, I have to take this one the other side and factor. So this is n by n matrix, this is x-s is a vector, equal b-us. You multiply both sides by inverse of this matrix. So x-s would be si minus a inverse b-us. Correct? And then you have the algebraic part, y equals c times x-s plus b-us. Okay? You already have x-s, plug x-s here, and you get y-s is equal to this. What is the transfer function here? Y-s equal h of s times u of s. This is your transfer function. So if you give me ABC model transfer function of that state space is what? C times Si minus A inverse B plus D. Okay? So go back and forth. Are we good? So this is transfer function. When engineers they think about the state space model, for them is this four matrices, A, B, C, D. That's the way they think. So give me A, B, C, D. This is your transfer function. Example. Do you guys want to do this example? Just like 2 minutes? I think you should do that, okay? Suppose I give you this, A, B, C. Do it. Transfer function. D is equal 0. So it would be what? C times Si minus A inverse times B. Can you do it? Would you like to try?
Yeah.
No, I'm talking to you. Get the transfer function. C, let's see. And then you have Si minus A inverse. And this is your B, is 1, 1. A is it readable for all of you guys? Minus 5, 1, minus 6, 0.
S is just it's one. S is just plus this variable. Or no, I'll say plus space. Okay, this, it's good.
Little s.
That's all.
You did inversion of a 2 by 2 matrix, right? All of you remember how to invert 2 by 2? Inverting a matrix is difficult, okay? But 2 by 2 is trivial. Swap the diagonal, change the sign of diagonal divided by determinant. If you don't remember, that's fine. I'm gonna just let you know. The inversion of a matrix is, complicated, but 2 by 2 is trivial. So when you work for 2 by 2, let's go through. So this HMS is CSI minus A. C is a 1, 0, okay, with a T. SI is this guy, minus this, and you have to invert it, times B. Is that okay? Up to this point? C, this is SI, this is SI, this is minus, this is your A, SI minus A inverse, times B. Is that clear? That's the first thing you should write. Okay? What is this guy? How do you make this? This would be 1, 0. This 2 would be what? Minus plus minus plus, so it's plus 5, first element. This one would be minus 1. 6s. Are you good? Inversion of this. This is your transfer function. Now you have to invert a 2 by 2 matrix. Okay? This matrix 2 by 2 matrix. You have to invert. Are you good? Or you're writing?
Sorry. Okay, fine.
Yeah. Okay. Yeah, so what is the 2 by 2 matrix? Can you just learn this? Write it down. This 2 by 2, A, B, C, D. How do I invert that? Swap the diagonal entry. Swap them. Swap them. Change the sign of off diagonal divided by determinant. Determinant is AB minus BC. Boom. 2 by 2 matrix has to be in your head. It's not like, okay, because you end up with second order system all the time. You have to be very good in just 2 by 2, okay, inversion of it is trivial. Then if you know this, okay, this is what it is. Okay? This is the swap version of it with the change of sign. Look at this. So what I have to do, I have to swap this guy, S plus 5 come here, S goes the other one. You see? S plus 5 here, S goes in that. Change the sign. This would be plus, this would be minus. Divided by determinant. Determinant this time, this minus this times. So you get this. That's your HLS. So, we learned transfer function, we learned a state space model, we go back and forth, no problem. You can go from ODE transfer function to state space. Let's do one more example so that we can be. If you guys writing this, just stop me, say, wait. Good? Okay. Can you guys do this? In this class, I want you guys to do this, okay? This class, you guys, you sit here and design stuff like that. It's the beginning, I will tell you. 10 minutes design of something. So, you have to work. It's not going to be PowerPoint formula, blah, blah, blah. It's about doing things. Okay, that's what we want to do. So suppose I give you this. I said, do the state space model for this system. Okay, first of all, my input is this source. And also let's say this I1 is an output. Okay? So that's what we need to do. Kirchhoff law first. Okay, Kirchhoff law first. As an engineer, when you look at this, how many ODE do you think you need to have?
3.
3. Absolutely. Engineers, they look at, but you have 3 dynamic elements here. Okay, I need 3 ODE. Get the 3 ODE going first. This loop current, I call it I1, I2. I choose my I1 to be my output. I'm concerned about that current. So this is a system I'm driving an E, and my output is I1. But first we have to write the ODE. 3 ODE. You want to find transfer function, you want to find a state space model for this device.
How much forms to do? We'll go on to very multiple components. 1, C is 2, 2.
You guys get it? You guys, anybody got it? Shukran? This is an extremely simple RC network, and you guys have to really be good at it. You have to say, you have to live with this for 4 years. Okay, let me show you. This is 3 different other questions. Right? It should be crazily obvious. You have capacitor and inductor. Obviously, you need to be able to just write it up. You should fly. Okay? This is a person with these guys. This is the current. So first for this, end up with the ODE, the constant fusion. So try to pull yourself up regarding writing secrets and checking a secret. Engineers, they see this and then they don't put a pencil on a paper. They know what this thing is. Okay? All right. So this next task. So we got the ODE. There are 3 ODE. So I'm asking, now I want to get the state space model. What was the roadmap? Roadmap was, what data do I need for this circuit? You know, if somebody gives me input, which is E, what else do I need to know in order to solve all this ODE? When you look at the circuit, it's always voltage across capacitor at the time that you start, current through the inductor at the time that you start. So look at this. First of all, look at this one. For this one, you need what? Voltage across capacitor, which is EC at the time that you start, 0. So EC should be one of the state. You're right, EC is one of the state. Okay, from here. How about here? It's the first order ODE. So in order to solve this guy, what requires? I1 at time 0. And then also for the other one, I2 at time 0. From engineering perspective, hey, I need to know the voltage across capacitor current through the inductor, otherwise I cannot solve this guy. Okay? So your state model is a 3-dimensional. You write x1 equal EC, x2 equal I1, x3 equal I2. Look at the evolution. Take a derivative of it and do it. Am I making sense? You guys need to do this. Okay? Here we go. I choose I1, I2, EC, and then take a derivative of it, this dot means derivative of this dot. This is your A matrix for this circuit. Write it down. The remaining is in the next page. First, I want you to write it down. Now we get a state space model for this device. X dot equal AX plus BU. So your X, sorry, this has to go out. The state, as I said, the I1, I2, and DC. Okay? X dot equal A, this is your A matrix. Okay? And then later on, you guys do derive this thing by yourself and check out. You have this equation, so ODE, now we go to a state space model. I choose the state and I'm good to go. A times X, your A matrix. Plus, which I didn't have a space here in the next page, but you're done writing this, I can put in what is our B, what is our C. Are we done with this? B plus B, U, U is in. This is your B, B, it is your input, right? And I choose I1 to be my output. So if I multiply this one by this is your C matrix, it picks up. We got the state space model for that. Y equal 1, 0, 0 times your state, which is I1, I2, DC. That's the state model of that device. You don't need to memorize anything. You don't need to do anything. Just write the Kirchhoff law and ask yourself, what data do I need to solve this? Those are state. And take a derivative of it and just you're good to go. Make sense? Okay. Now, transfer function for this device. You have ABC, means what? C times Si minus A inverse times B. Okay? C times Si minus A inverse. I got it this. This is a 3x3 inversion. How many of you know how to invert the matrix? 2x2 I showed it. Suppose it's 3x3. Learn this stuff. Don't say, I'm going to plug in MATLAB. I said, no, engineering doesn't work that way. I hate to inform you, engineering is at the back of the envelope, it's at the head of the person. If you want to work, doesn't work. You have to see things. Now we go, like, for example, as soon as we go to frequency domain, we want to design, you know, you see a device, the body plot has to pop up in your head, how this device, you know, frequency response is, etc. So just learn a little bit of, you know, how to write Kirchhoff law for RLC circuit, etc. or mechanical. Homework number 1, there are good set of problems in your textbook. There is 10 problems that you have to do. Do it by yourself. Sit on it. Do not go to your internet to say somebody else has done it. I can only copy. Copying means nothing. Zero. In fact, copying the solution from the internet, putting it there, you're damaging yourself. It works negatively. Trust me on that. When you start working, you understand this. Okay? It's all going to show up very first time that you interface with job market. Okay? All right. So, is it fair to say that you understood transfer function and state space model, right? We standard stuff, you do some problem, and you see, Okay. Now the next model for us is the impulse response, right? Impulse response. Let's motivate why they use why engineers are doing the impulse response. That's an interesting question as well. So, how many of you know exactly delta functions, the way it's defined? Go ahead.
The delta function is, or I'm assuming the Dirac delta function. Right?
You assume what?
The Dirac delta function, right?
Delta function.
Yeah.
What do you know about delta function?
That its integral is, it has an infinitesimal with infinite value at 0, and that its integral is equal to 1.
So, delta function, actually, remember this. First of all, it's not a function. Okay? It is so-called generalized function. Or another word for it is distribution. It is used in an undergraduate in a certain university like ours, for example. Can we come up with an approximation of delta function that makes sense? And in fact, it's good approximation and is sufficient. But if you want to go further, you have to learn so-called generalized calculus and generalized function. Remember what is function? Function means you have a domain and you have a range. You pair them up, right? You pair them up. Like for each member of the domain, you assign something here. It's pairing up. Okay? You have to be careful. Function has a structure. Like think about it like f of t. T is a set of real numbers. The other one also set of units. You assign something from the range. Let me come up with a metaphor for it. Husband and wife. You know, various pairing up. It's called husband and wife. Okay? Domain and a range. You pair them up, right? It's called marriage, right? But there is a structure in the function. The husband can have zillions of wife. Wife cannot have 2 husbands. In other words, you cannot assign 2 elements of the range to the domain. Like if I draw something for you like this, let me just, if somebody draws this thing for you, that's the domain, this is a range. Is this a function? No, because this guy is paired up with a 2. It's not. But think about a step function. Everything goes to 1. See, like a step function would be like this. This guy is a husband of all. So function has a structure. You remember about it. But generalized function is not a function. It's not a pairing things. It has a different angle to that is a so-called distribution, so-called generalized function. But approximation is the following. A pulse, pick up a pulse. Base of the pulse, call it, for example, delta. The height of the pulse has to be 1 over delta. Pulse delta, imagine. So, let me see whether I have it here. Look at this. A pulse, you put that on T1, base is delta, and 1 over delta. Is that clear? This pulse, as the delta is small, it acts like a delta. It's a good approximation for the delta function. Is that clear? A pulse at base is teeny tiny small. Why is so significant about this? So we refer to this. If I put a delta here, that means this pulse. Now, if the delta goes to 0, what do? In undergraduate, they put an arrow. You remember, arrow goes of what?
Yes.
Whatever. Arrow doesn't mean at that point it's infinity. Don't say that, because it's not a pair. Arrow means some other animal things that we don't know. It comes in generalized function, okay? So the best way to think about delta function, you can say, is a pulse, base is delta, height is 1 over delta, as I have here. Put it at any point. It's a pulse at t1. If delta goes to 0, we call this the delta function. It's a good way to understand this delta function without getting into the mathematics of it, etc., etc. Okay, are we good? So that's the definition of a delta function. Obviously, if you integrate this is equal 1, because it's 1 over delta, delta always, no matter what is the delta, the area of this is trivially 1. But a pulse with this base and this height, okay? As delta goes to 0. Okay. So, as this property, is 1, no matter what is delta, if you take a delta equals 0, limit goes to 0, means reduce it again is 1. We can always think about the integral of delta is 1, for obvious reason, with some definition. So that's the way to think about delta. But what is so significant about delta? Why engineer picked up a delta and response to a delta, they refer to it as an impulse response? What did they do this? Why didn't pick up like a step function, respond to a step function, or some other function? What's so peculiar about delta? What is the strange property of delta that allows you to utilize it for modeling? Okay. It turns out delta it is an interesting object. If you give me, I'm going to show it to you, it's trivial to show it to you. If you give me any arbitrary signal, arbitrary wave, whatever it is, okay? Essentially, mathematically can be viewed as infinite weighted sum of zillions of a delta sitting at various. Make sense? Essentially, think about it like this: weighted sum of infinitely many. Try to understand the idea. Okay? If any artificial signal is a weighted sum of zillions of a delta, okay? What's good about this? Think about linearity. Remember linearity is what? Superposition. Superposition tells you if you have a weighted sum, response would be what? Weighted response of the so if any arbitrary signal is a weighted sum of delta, then maybe if I know the response to delta, I can find response to any arbitrary signal. Is that clear to you? Do you see it?
Yes.
That's the logic that impulse response shows up. Remember this, and I'm going to show it to you. Any arbitrary signal is really weighted sum of zero. If that's what it is, hey, if I know the response to the delta, I know the response to anything. How do I get it through the convolution, etc., blah. This is a rodent. This is why of it. Make sense? And then we will figure it out. Okay, this is what it is. I don't know what. Maybe the history of the Boeing is that I haven't checked my impulse. So if it's not today, I don't know what has happened. They were supposed to be here at 9:50. Now it's 6 or so. I'll check with them to see what it is. Now think about this. Think about this. This is an arbitrary signal that I do, some f of t. This is your delta sitting at time t1. Delta is a pulse. Always remember a pulse. Narrow base height is 1 over delta. Base is delta, it's 1 over delta. Okay, let's multiply these two and integrate. Okay? Since it's 0, kills this signal. Okay? When you multiply, the only things that you have is in this little base, because the rest of the multiplication is 0. So you get this. This becomes equal this. can we approximate this guy? So delta is very small. You multiply this in these things. So obviously you can say if I multiply ft by this delta, the base delta, I can approximate as like 1 over delta times ft. Is that clear? You see it or not?
Yes.
Yeah.
Yes,
Because that means like this, right? 1 over delta times the value of this guy. Since delta is teeny, take the value of this equal to t1. Okay? So you have this. And what this one gives you, so instead of this, I'm going to put this guy. If I put this guy, I get this equation. This equation. ft1 equals this. Okay? Because when you put this guy 1 over delta ft1 comes out of the integral 1 over delta, you integrate 1 over delta in the delta interval, it's over 1, so essentially it becomes this. Make sense? Do you see it, everyone's? Okay, you have this. Now try the following. Okay, this is what it is, this is what I need. Since we are using input to the devices as a U, let's just call that U, for example. We change it. Running variable here for the integral is t. Call it tau. And t1, call it t. Doesn't matter for anything. So what you get this. Get this. Any signal is equal. This is a convolution operator. You can convolve them with the delta and you get it itself. Just stare at this stuff. What does this mean? Can anybody tell me what this equation means?
the convolution of a function with.
No, I don't want convolution. I just want idea. What does it mean? Obviously, it's a convolution. I don't want to read the convolution. Of course, it's a convolution. What does it mean?
Adding up all the delta.
First of all, what is this guy? This guy is integral is essentially sum. Do you see it? Okay, let's look at the idea. Integral is a sum. What does it do? Sum.
Honestly, this class is terrible.